But here, it is my privilege to introduce Steve Salerno, my friend of a long time, who is an amazing hacker who has accomplished quite a bit, and he's going to talk to you here about Android WLAN drivers. Take it away, Steve.
Thank you, Jay. So if we had more people here, I would ask how many people are new. But since I think I may actually have more bugs than there are people in the audience, we're going to skip that one. The main goal of this, though, is to kind of talk about some research I do in my free time and kind of give it to the newbies who either want to find their first bug or want to do their first bounty, whatever they want to do. And really, I hope to kind of convey this information, hopefully well enough, that you can essentially take this, find your own bug, report it, and the next time I submit, I hope to be stumped by one of you folks. So we're going to hop right in. The story kind of starts about a decade ago. I joined QPSI at Qualcomm, which is the product security team, fresh out of the government. When I was there for about a year and a half, I focused mostly on the WLAN host driver. It comes in roughly 3 flavors on Linux. There is a Windows host driver as well. Didn't look at that. I don't even know how the Windows kernel works. So of those 3 kind of flavors, there's Primo and Pronto. Prima is the driver name for the Linux host kernel. It's mostly deprecated on really old devices. You probably won't see it anymore these days. And then Pronto is the corresponding WLAN firmware that runs with Prima. And then we have QCACLD 2.0, 3.0. Don't ask me what the acronym actually stands for. At one time I did know, I no longer know. 2.0 is like the kind of minimal base set of features. It's mostly on low-end devices, again, kind of older devices. These days, I'm not even sure it's being released anymore. And then 3.0 is kind of the high-tier, premium-tier flagship products. And that's the current hotness, and if you're going to be looking for bugs, you want to look at that driver. I think in the actual source code, though, you will just see QCACLD and not the numbers. Also associated with these drivers are multiple different firmware variants, and they generally differ depending on what the actual hardware of the WLAN chip itself is. So there shouldn't be anything super crazy new on kind of the attack surface side. Everybody's sort of familiar how, your traditional Linux kernel drivers have kind of a pretty big attack surface from user space. So you have all the same things a normal driver would have, like sysfs, procfs, debugfs. You also have iactls. So in WLAN, they call them wireless extensions. Those are mostly just used to kind of configure WLAN, do like interface management, scan the network, associate, dissociate, auth, deauth, stuff like that. And then maybe do more advanced things like, say I want to blacklist this SSID, or I want to look at these channels, et cetera, et cetera. One you might not be familiar with is CFG 802.11. I'm not going to cover that right now because the rest of the talk is about that. The unique thing to WLAN that obviously a lot of other drivers don't have to deal with is obviously the OTA route, right? So your holy grail, in most cases, if you're doing offensive security research, is you want to get that zero-click OTA bug from some remote pre-auth, get straight to the kernel, code execution, and then do whatever you want to do. These are certainly plausible in WLAN. The host driver itself doesn't do a ton of processing of OTA data. It does a little bit. But for the most part, most of the data just kind of gets passed up the stack and then given to something like WPA supplicant to handle and give to the user. But those attacks certainly exist. There's also the more just a common case where you have the OTA case and you may land on the firmware, right? So this is something like Broadbone where your actual code exec is on where the WLAN chip itself is, and then you need to pivot from WLAN firmware to the AP, and then from the AP to wherever you want to go. Landing on the firmware gives you a little bit more freedom in terms of your pivot, right? There's a ton of different APIs that kind of go northbound up to the application processor. And then you have other things like, older phones have DMA, most new things have PCIe, but there's just a wider variety of things you can do because you have much easier control of the data at that point. This is 10 years, give or take a year, of WLAN issues for just the kernel host driver and firmware driver, or firmware. Blue is the host driver, red is firmware. Some important caveats here is that kind of the time prior to that really big red spike, Qualcomm wasn't issuing their own security bulletins. It was basically just Google doing all of the security issues for all the OEMs at once. And so you would oftentimes see, there's a bug in this Qualcomm closed source component, and that is all you would see. You would have no idea as to, is it in WLAN? Is it in the modem? Is it in some other proprietary component? Don't know. So there's not any real good data prior to that in terms of WLAN firmware issues. Certainly they exist, but we don't have it. The other important note is that some internal issues don't get published in the external security bulletin. There's a variety of reasons why this occurs, but effectively, this data is going to be an undercount of the actual total issues that exist in the driver and the firmware, right? So like when I was there, I started a little bit before that red spike, and then I left about where that other kind of spike is. But a lot of my issues aren't going to exist in that time frame because, right, I reported them, it takes time to patch, and so you'll see kind of this slow decay. But I can assure you there's way more issues than up there. So for the rest of the talk, we're going to talk about CFG 802.11 and what it is and why nobody knows about it. Just a quick note, so CFG 802.11 is one thing, NL 802.11 is another thing. I don't actually know the difference between the two of them. I'm going to probably use them interchangeably. If you're mad about it, I'm sorry, and maybe you can tell me what the difference is later. Just a quick caveat. So, quick overview. At some point, Linux wireless community decided, we don't want to do wireless extensions anymore. I don't know why. I don't know if there's drama. They just decided, and then at some point, they basically replaced that entire API interface with CFG 802.11. So what this means is effectively, all the things you can do with iActls, both public, private iActls, were put in maintenance mode. You weren't supposed to do new feature development on it. They're done. You can patch them for security issues, but there shouldn't be anything else new there. And then all of those features should be replaced with this new CFG 802.11 protocol. And the only difference here is that iActls, generally, you just create a socket, you talk to the file descriptor, you push some stuff into the kernel, good to go. These use netlink attribute buffers. So in this case, you're going to create a netlink socket, create a giant buffer, and then just shove that buffer down into the kernel. And they all kind of provide the same sets of APIs for you to do things like configuring WLAN, things like that. The code snippet on the bottom shows just an example of how in the kernel you would specify one of these commands. So for us, there's only really two things we care about here. The .command field basically is just an enum. You're going to specify that for this is the command type I want to use. So in this case, this is this NL802.11 command start AP. It does exactly what you think, which is it starts the driver in access point mode. And then the only other really relevant thing is the .doit, which is a field that is a callback handler. So basically the kernel combines these two and says, okay, you send a message for start AP. I'm going to call NL802.11 start AP, pass in the data, and then go from there. So this is a poorly drawn version of netlink buffer. They're basically just length type value try states, and you just combine them and concatenate them, and then you send them down. So in the kernel, you'll see this struct NL adder definition. The first value is a length, the second value is a type, and then you would append any data after that for however long the data is. Obviously, the length has to be the length of that buffer. And then you just kind of keep appending these for whatever you need. The neat thing about this, though, is that you can certainly do this, but you can also do this, which is inside of the data for the first one, you can nest in another NLA buffer inside the data. So you can do this weird like inception level thing where you've got nested buffers inside of nested buffers inside of nested buffers, and you can only imagine the hell that this rots. Because if you're going to do validation on maybe that top level buffer, that's good, but you just miss validation on the nested thing inside of it. So at every level when you're pulling data out, you need to validate the data at every single level. These are some common APIs you're going to see in code that's handling the parsing and callback functions for NL8 802.11. They're defined in some like netlink.h kernel header. There's definitely more than what's up there on the screen, but these are kind of the ones that are relevant to most of the work that I do. So NLA data basically returns you a pointer to that payload buffer that you pass in the buffer. NLA length basically just returns you the length that you specified. There's a weird little caveat here that NLA length, the function definition itself returns an int, but as we saw in the previous slide, the actual value for the length is a U16. So when you're auditing code, that's just kind of important to know that it is kind of capped in terms of the size, and it makes some integer overflows a little bit more difficult to do because you are capped at U16 rather than like max int. You have a bunch of accessor APIs, right? So if you send in an NLA buffer and you said, hey, you know, this type is going to be a U32 because I'm going to use it as a flag or an index somewhere, then you would call like NLA get U32, pass in the buffer, and then it would output the U32 that should be in your data. Caveat here is that these functions don't really validate the data, right? So if I said, you know, hey, get a U32 from this thing, all it's going to do is it's going to go to the data payload pointer, cast it to a U32 because you said it was a U32, and then return it. There's no validation to be like, hey, you said U32, so it should be 4 bytes. Let me make sure that's the case, and you know, return an error if it's not the case. There's a classic like memcopy and memcompare as well. The memcopy is actually safe. So you know, if you try to put a length that is maybe too large or too little, it is going to compare it to the actual length of the attribute. So there's some safety checks there. I believe that's also the case in memcompare. And then the last three kind of function definitions or APIs that we care about are these attribute parsing guys. So NLA parse is an actual function. You give it the buffer, you give it the length, and then essentially what it does is it returns you a dictionary of the data. So the key would be the attribute type, and the value would be a pointer to the buffer payload, or the payload buffer for that corresponding attribute. The other two, NLA parse nested and NLA for each adder, are actually macros, and are essentially just kind of iterators through. We're going to start at the front, for loop through, and then we're going to return you an iterator for each one of the entries in the buffer itself. There's another important caveat here between like NLA parse and an NLA parse for each, and that is, right, NLA parse returns you a dictionary, which means if you have, or if you send it a buffer payload that has multiple attributes of the same type, so like foo, bar, foo, only the last foo will be put in there, right? Because all it's going to do is it's going to say, here's the key for foo, and it's just going to keep updating the value with whatever the last thing it saw. So that means if you're trying to do tricks by sending it like multiple attributes to maybe change how some logic is flowing in one of the handlers, you have to be aware that you only get one chance, or only the last value is going to matter there. On the other hand, NLA parse each adder is just a for loop. So it's going to parse the first foo, and it's going to parse bar, and it's going to foo. So in that case, if there's any sort of logic that's kind of time of check, time of UC, where you grabbed a value and then maybe you do something with that value, and then you expected that value to not change, and they use this function, it's probably a bad time. NLA policy is an optional argument given to NLA parse. So when you NLA parse any kind of buffers, you can provide this optional argument, and basically what this allows you to do is for any set of attributes you pass in, you can specify a type for the attribute, and you can specify a length for the attribute. These are all handled in different and fun ways, though. So for instance, you can have an NLA null string. This will guarantee you that the string that is returned has a null byte. However, the null byte is accounted for in the policy validation. So that means like if you say, I expect this thing to be 10 bytes, then what you actually need is 11 bytes, because it would be 10 bytes for the buffer, and then the 11 bytes would be the null byte. NLA string, on the other hand, don't give a damn about your null termination. It's just like, you said it was a string, I'm going to trust you, I'm not really going to check it, and then return you a char array. NLA null string, NLA string, and NLA binary, when you provide a length type, are specifying a maximum length. So that means, if I said I want to use an NLA string and it's 10 bytes, and I gave you some data, it's going to guarantee that that string is less than 10 bytes. NLA unspec, on the other hand, which is the default type for all things that don't have a type, if you provide a length, it's actually a minimum value. So if you said, hey, I have an NLA length of 6 bytes and it is NLA unspec, then you need to give it at least 6 bytes, otherwise it's going to throw it away. And you can kind of see that the bottom is an example of one of these policies. Most of the things in there are just like integers and booleans and flags like that. But I think that the bottom two are basically MAC addresses. And so in this case, you would specify their NLA unspec, and they have to be at least 6 bytes. And that makes sense, right? Because you have 6 bytes for a MAC address, there should be 6 bytes. And if you had them as NLA strings, that would be a maximum length, and so technically you could provide less than 6 bytes for a MAC address, and that just doesn't make sense. you're doing any sort of CFG 802.11 coding, all I can say is use this. It makes it so much harder. It's not impossible to still find issues, but like this should be the minimum bar. Like almost all of the Qualcomm code uses this. There's still bugs, but it uses this and it's way harder. The Samsung code we're going to see, this doesn't exist and it's a field day. So let's look at a real quick example. So this is that start command function that we saw earlier. This is the actual function call that would come back when you specify it. And there's three quick things we want to look at. So this first pointer that comes in as an argument is this gen_l info structure. This is populated by the core kernel way prior to us. It's going to do its own NLA parse all the data, and then inside of there's an adders field. It's going to basically slam a pointer in there and say, here's all your parsed data, good to go. And if we look a little bit lower, we can see, this code, for instance, is actually looking at info adders. It's checking to see if this beacon interval, this DTIM period, and this beacon head, if each of those attributes is present inside of your buffer, because those are mandatory arguments for start AP. And then if they're not, you're going to error out. Just past that, we can see a call to NLA get U8. All this is going to do is go to this adder SMPS mode, pull out a U8, and then it's comparing it against some other value. And if it doesn't equal that, then not supported, return an error. So basically what this command is just doing is, basic sanity checking of, hey, these attributes that I require are there, and the fields that I think should be there are sane values. And then the last thing we're going to see down here is this call to RDev start AP. RDev is like this holistic agnostic wrapper around a bunch of APIs that is essentially just going to parcel data down to the firmware. And so at this point, what this function has essentially done is you've copied all the data in from user space, you've done some light validation, and you're going to ship it off to the firmware, and the firmware is going to do more things. So this is great. There's a bunch of kind of core APIs that do this stuff. But back in the days with wireless extensions, we had private actals, which just let us do whatever the hell we wanted to do. So what if I want to do that here? Well, they're like, let's do that. So there's a NLA 802.11 command vendor, which is basically just a vendor command. This lets the vendor say, hey, here are all the core features I support, but if you want all this extra stuff, call here, and then we're going to do some weird things. So on here, it handles it a little bit differently, which is we're going to come in here, we're going to grab two attributes, one of which is adder vendor ID, the other is a vendor command, vendor subcommand. These are basically just, I think, like U32s or U8s. We're going to take that, we're going to loop through all of the known vendor commands that we know about and try and find out which one of them you just specified. And what the vendor commands are going to do is they have that same kind of like do it command structure that we saw on the first example. A vendor command can have their own array of all those structures. And so we're just looping through that to find which callback function we actually need to call. After we find a valid callback or a valid supported command, we're going to go to one more attribute called vendor data, which is just a nested attribute pair. And then we're going to pull that out, and then we're just going to call the callback handler that the vendor told us to call. And so this basically just lets you say, here's an arbitrary number of other functions to call that are outside of the norm. So this is a quick example of what a vendor command in Qualcomm looks like. It's this like set TX power scale decrement dB. No idea what that actually does. But so for us, all we really care about is those last two parameters are the nested attribute buffer that we sent in. So like if you're doing static analysis or code review, you start here, and you know those values are tainted. You control every part of that buffer. From here on out is what you need to review. We can see that the first thing it's going to do is call NLA parse because the kernel didn't parse this data, it was nested. So it's going to come in and say, hey, you're giving me data, I need to parse it, I need to look at it and validate it. This is Qualcomm code, so you can see the last argument here is TX power scale decrement DB policy. So they are specifying an NLA policy that actually does the further validation of the actual input when it's parsing it. We see another call to get U8. In this case, we're grabbing TX power scale decrement DB. We're making sure that it's in the input that you gave us, and if it's not, we return an error. And then finally, we call WMA set TX power scale decrement DB. WMA in the Qualcomm kernel is just going to be a southbound path to the firmware and says, hey, parse this data, I validated it, did whatever we need to do, looks good, firmware take care of this. And again, if you start looking at this code, you basically just need to find these function handlers, and you can start doing static analysis from here. So let's take a quick example of what this looks like in a real bug. So this is a bug I reported long after I left Qualcomm. I had some free time and was like, let me see how things are going. And so let's take a gander. So this is the subcommand roam vendor command. This doesn't do much, at least in the beginning, except for 2 or 3 lines prior to this, you'll see it called a QDF memmalloc. It's just a wrapper around a KZalloc. So we're going to heap allocate some stuff, which in this case is RSO config. And then we're going to pass that and our data pointer to another function. In this case, we're going to call NLA parse again, parse the data again. This has this WLAN CFGA 211. That's just a wrapper around it. I don't know why they need wrappers around wrappers, but somebody's got to get lines of code in the kernel. But ultimately, just treat it the same. What we care about in this flow is this adder roaming subcommand. So like we're doing a subcommand in a subcommand for this example. So this is going to pull out a U32, assign it to the command type, and then just below, it's going to take that command type, use it in a switch case statement, and decide, oh, it's this type of command that we need to handle. And so what's going to happen here is it's just going to take our data, send it down another layer. All of this data is again nested, so we need to parse the nested TLV. So we do that. And then there's some light validation to make sure that there's this param freak list scheme. And if that's there, we're good to go. We can call the function and parse it. That thing is once again another nested attribute. So at this point, we're like 2 or 3 layers deep. We again revalidate it. You can see, I didn't put it in the last slide, but there's a different policy for every one of these function calls. So in this case, it's roam scan freak list scheme policy. And that's just to validate the data at each nested level. Here we see our first call to the NLA for each nested macro. So what this is going to do is there's this param scan freak list attribute, and the intent there is that you're going to say, hey, this is this attribute, and I'm going to have a bunch of these because I'm generating a frequency list that I want you to do something on, probably a scan on because the function name. And all I'm going to do is I'm going to find each one of those attributes inside that buffer, and I'm going to increment this numchan value. If you look up at the top, it's not highlighted. you can see numchan is a uint 8. And then just below the lower portion of this box, there's going to be a quick validation to make sure that this value is not greater than some random max value. So like that value is pretty easy to overflow. We only need to send 256 of those. We then wrap around. We now have 0 channels in our array. And that should easily pass validation because that's less than 96. And then rather than looping over numchan, we call the same for each nested macro again, which is going to go and look through all of the attributes, which are definitely more than 96. And we're just going to result in a buffer overflow because we've copied way more data than we should have. So I think the fix here was like, I think they jammed it all into one NLA for each nested macro, and then just a sanity check of like, hey, if we ever hit greater than 96, bail out of this loop. There was absolutely no reason they needed to do like loop, check, loop, and so the function was just inherently broken. That was all Qualcomm stuff. So kind of the back half here is going to be Samsung. And so after leaving Qualcomm, I kind of had like downtime, and I was like, I'm going to do freelance research, I'm going to do VRPs, and I'm going to kind of do my own thing. But fundamentally, I had to make a decision, right? And I think this is kind of a decision most of us as researchers have to pick, which is kind of a breadth versus depth approach. And that is, the classic VRP or bounty program is I need to find as many bugs as possible in as many things as possible because I have to make the most money. Versus like your more company-oriented research and kind of nation-state research, which is I want to focus on this one thing. I want to find the one bug that nobody else can find because they don't understand this thing. And it's going to live forever because nobody will ever find it. Well, for me, that would be great. But like if I've got to live off the bugs I find, that incredibly complex bug, unless I sell it to unscrupulous people, is going to get me maybe a couple grand in a bounty program, right? Cool. Or I could go and just pound on drivers and drop like 20, 30, 40 bugs. Maybe they're worth a little bit more, but I'll ultimately make more money there, right? And so I decided to go kind of a mix in between. So I was looking at a bunch of Samsung code, and I stumbled upon, hey, they've got their own driver for WLAN. As far as I can tell, this is like low, medium tier Exynos chips. Your higher tier stuff is either going to be Qualcomm chips or Broadcom chips. Wasn't doing Qualcomm stuff because I just left there. Broadcom's weird. I didn't really want to deal with them too much. But I was like, let me start poking here. If you've looked at Samsung code before, you can imagine what's going to happen next, which is almost every single command handler they implemented had at least one buffer overflow of some form or multiple overreads, and it was just like shooting fish in a barrel. So we're going to go over a few of these. We'll probably skip one or two. Actually, we'll skip the first one. But these slides will be public and the talk's public at some point. So this is the gscan set OUI vendor command. I have no idea what it does. I don't really care. At some point, we're going to call NLA for each adder. At the bottom there, you can see there is no NLA parse. There is no policy validation here. They're just going to go ahead and call their for loop. And in this case, they're really only looking for one attribute, which is this P&O random MAC OUI. It's like, hey, it's expecting a MAC address, which should be 6 bytes. Copies in 3 for some reason, which might actually be a country code. There's no validation on that. You can send in whatever you want, so 1 byte. So this is like a small, like possible 2-byte overread. Absolutely useless bug, but these are essentially everywhere, right? Because if you're not doing any validation, you're almost always going to read more things, read over more data than you expected. The second case, this is a keep alive offload vendor command. We'll skip through it real quick, but this is another case where, you know, we're going to call the macro. We're looking for this keep alive attribute ID. We're going to put that value into index. Index is a U8. We're going to YOLO, live free. We're not going to check that value at all. And then we're just going to write 0 to it and hope everything goes well. So there should be a relative write of 0 to anywhere. There's a read before it. But again, probably not exploitable, probably not super useful, just because of the bounds of it. So I reported all those bugs. That took about like 3 months. And then I stepped away from this code for a while. That's for 3 reasons. One, you know, if you've worked in product security before, it's going to take them a while to patch the bugs. They're patching code. That means things are going to shift around. Depending on how they patch it is going to be dependent, is going to change on whether bugs later are feasible or not, or whether they even still exist. So I didn't want to deal with the code churn, so I just sort of stepped away. There's also 2 other interesting points here, which is, you know, there's times where the product security team can step in and be like, this code sucks. You need to fix this. And so they could have easily stepped in and been like, yo, use NLA parse, use a policy, start validating things. And they could have spent like a year doing that and then had fewer bugs. Spoiler alert, they didn't do that. And then the third thing they could have done was security could have been like, man, this guy just dropped like 20 to 30 bugs on us. Maybe we should take a look at this and prevent this from being an issue in the future. They also didn't do that. So in like early 2024, I had some free time, went back, and submitted 3 more CVEs. So the first one is just another array index. It gets 0 initialized, but they never mandate that the thing that sets the index value has to be a required argument. So it can just stay at 0. They subtract 1 from it, and then just go to town. So that was easy. I think there were like 2 of those. There's this interface create, interface delete function, which takes in an interface string name. Should be null terminated because they do a bunch of string operations on it. Nothing guarantees a null byte. So you can just buffer overflow and buffer overread as much data as you want there. The more interesting one is the last bug. And so we'll see it in another slide, but is the most brain dead buffer overflow you're ever going to see. And like, this is something they teach in like computer security 101 classes. But I reported it and they're like, hey, we've already patched this bug. And a Chinese researcher who's often in this area as well was credited with the reward. And so I was like, that's weird. I know he's done this before because he submitted a lot to Qualcomm, and he doesn't know this, but like my job was to basically prevent him from getting as much money from Qualcomm as possible. And so he got one over on me here. But I was like, that's weird. Let me step back and figure out why this is a thing. And so I kind of did my own self-reflection and kind of came up with 2 reasons. So one, at some point between the first set of bugs I submitted and this set of bugs, the program I had to submit to moved from Samsung Mobile Security to the Samsung Semiconductor Product Security team. Those apparently are 2 different corporations. They share no product security teams in common at all. I don't even know what they're technically responsible for, because if you go to the security bulletins for both groups, you're going to see some overlapping stuff and then some unique stuff. But all I know is that apparently Samsung Mobile can't buy DRAM from semiconductor, and they're upset about it. So that was a problem because I was basically looking over here at this product security team for bugs and reports and wasn't seeing anything. And what I need to do was look at this other random company doing these other random bulletins, and I missed them all. And the other thing was like there's a bunch of weirdness with their kernel source. I'm not going to explain it now for lack of time, but they're doing weird stuff. So this is the bug. Our good old friend NLA for each adder. In this case, you have one attribute called adder app info lang. It's a U16. For some reason, they copy that out, and they're like, hell yeah, this is great. Let's just take that length you gave me, and then I'm going to memcopy. Like, I love just calling memcopy and putting all that data in a buffer that is definitely the length you just told me. And so this is obviously a bug. And so this was something the other researcher reported before me. So this is their patch. It's not super clear, but basically just before the memcopy, they validate, hey, the length you've passed in, if it's ever above this value, don't do the memcopy. This is a fix. I'm sure it's going to have other ramifications to the code base just because I'm more familiar with it. But I think a better check would have been like, one, you don't need that length attribute. That's useless. Just call NLA length and be like, hey, the thing you gave me was 10 bytes. I'm going to copy those 10 bytes in. Done. Like, why you're pulling a length out of a completely arbitrary other attribute is beyond me. But if we take a step back, so the top part is that first bug. If we look one line below that bug, they're doing literally the same thing with a different set of attributes. And like I racked my mind behind like why. But then on top of that, what I didn't understand was like, well, surely the other researcher saw this, and surely he reported all these issues. Maybe he missed it. But then, like, why didn't Samsung patch this themselves? I don't know. Maybe one day I'll meet them and tell me why. But I basically sat in this bug for a while because I wasn't sure if they're going to actually patch it. If they knew about it, they didn't know about it. And then there is one other CV that was in there that I did some like patch analysis on. So it's literally the same primitive, which is I'm going to copy this length out, and then I'm just going to memcopy. The problem with their patch, which is probably going to be hard to read from the back, is that the length check that they're using is for an entirely different attribute. So this value is SDEA service-specific info lang, which is an attribute pair that's in this function just later, but is wholly unrelated to this publish surface info attribute pair. So they put a patch in there. It literally doesn't do anything though, and so like the whole thing is still broken. So it came out to be there's a dozen more of those bugs. So the first two bugs or CVs up there are basically a combination of those 12 issues along with that bad patch. And then when I reported those, I reported two other issues alongside of those. They're not disclosed yet. They're just as equally dumb as everything else that's been covered in this presentation. And hopefully they'll be released soon. So real quick, just for like the new folks, I wanted to do like at least a brief overview of like VRP and how different they are across different companies. So these are the three that I'm most familiar with, and kind of some criteria that I think is relevant to each of them. The Qualcomm one is invite only. It's like a soft invite only. That's why it's in quotes. They have an email address with the PGP key that you can send bugs to. Scott Bauer runs the program. He's very easy to talk to, very easy. He cares about the program. He's kind of worth his weight in gold there. And if you get in contact with him, he's going to make sure that like you're taken care of there. The Samsung semiconductor stuff, if you submit them bugs, I'm going to warn you right now, the only way they pay out is international wire transfers, and that requires giving Samsung semiconductor, who's never been hacked before, all of your banking info. So if that's like a non-starter, I wouldn't submit to them. And then they also technically require POC for all of their submissions. I've never submitted POC. I'm just too lazy to do that. So they still pay out, but maybe they're just docking some pay for not having POC. I'm not sure. 2 other points. Some companies do charity matching. So if you want to donate to a charity, they'll take your bounty and donate it, and then sometimes match it. It depends on the company. And then from like my own perspective, if anybody's doing like policy or regulation, like this would be a great area to like invest some time in it. I have no idea how you're going to do it because this is just a hard problem, and like I don't think there's going to be one set of legislation that can help like these really big companies, but not like screw over the little guys, and vice versa. Quick summary. To quote the Android security team from 6 or 7 years ago, WLAN's still a dumpster fire. It's just because everybody does things differently. Nobody really cares. The CFG 802.11 stuff, most people don't even know it exists. So it's this weird kind of flying under the radar attack surface that nobody's doing static analysis for, or fuzzing, or doing anything like that. So there's just a lot of easy, low-hanging fruit there. And frankly, these things probably exist in a ton of different drivers because product security teams are just like understaffed, underpaid. They have way too much work, and like the world is out to get them, quite literally, right? So like I feel for them. It was a hard job, and more power to them. Anybody who wants to kind of take this work and expand upon it, Broadcom would be a great target. Like, there's definitely a bug. I reported one bug. I just think it's difficult to report the bugs because, like, who do you report a third-party driver to? Like, Qualcomm's not going to patch a Broadcom bug. Google's not going to do it. Samsung's not going to do it. I don't even know if Broadcom has a program. And then the Samsung driver certainly has more issues. So if you want some free money, look there. And then time? Jay? Questions?
What are there capabilities required for that NetLink interface, or are there any special SE Linux contexts that have access to it?
Yeah, so the question is like, are there any capabilities or things that prohibit it? I didn't look too much into it. Again, I'm too lazy to write POCs. As far as I understand, you definitely have to create a NetLink socket, which I think is like netraw or admin, which I think just the root user has. There may be some other things. Whatever WPA supplicant runs as, which may be like the Wi-Fi user or something like that, definitely has all the capabilities because it has to be able to configure the driver, right? And that definitely doesn't run as root, knock on wood. So yeah, like this is essentially a root to kernel. That's why they're kind of useless, and I don't care about this, but they're just kind of fun little weird bugs that exist. Other questions? Again.
Do you know if the hardware is required to load these modules?
Do I know if the hardware is required to load these modules? Yes. So if you wanted to like take this driver and try and slam it into QEMU and do like syscalor fuzzing or something like that, it would fall over because it's just going to need like GPIO map stuff and depending on how it talks with the firmware and some bridge over there. So that doesn't behoove you, right? There's been talks about how KGSL and Mali have been emulated, so you could probably use the same sort of techniques there and just do it for WLAN. I'm, again, just too lazy to do that. Cool. Thanks, guys.